Kevin Hart. It was just special. They don't have it.
Oh, yeah, they don't.
It really upset me because I watched it one night. I went to search for it the next day, and it said it had been taken off because of recordings.
Yeah.
Okay. How'd the last assignment go?
Good.
I believe you, Jared. Awesome.
Oh my
All right,
God.
I need to get your guys' more of the assignments recorded because, of course, we're coming to the end of the grading period.
We do
And I
it
hope.
Thursday.
What?
We do it Thursday.
Yes.
Jared, what the heck?
Jared, do you have them done?
Not all of them. I have them started. but
I'm
not-
always impressed. Jared actually always has more done than you think he does. Like, he kind of makes it look like he hasn't actually done much of anything, but actually, whether he has at the present time or there will exist a time in the future that Jared hasn't done, one way or the other, it gets. I mean, I'm kind of impressed. It's okay. It's a thing. It's a thing. All right. All right. Would a list of the assignments be useful?
Yes.
All right. Well, I can send it.
Can we actually like get that like posted on like It's Learning, like updated every
I don't have any way to do It's Learning. I don't know.
Check that anyway.
Can you? What about? All right. So you know how you have that spreadsheet that has all of our
Uh-huh.
students on it?
Uh-huh.
Could you send that to us? in
No,
an
because it
email?
has also your grades on it. But I could send it to. I could find a way to put it on like a clean spreadsheet that doesn't have grades,
Yeah.
and then just send it to
do
you.
that.
I could.
All right. 'Cause
That would be
help out
like
with
a
the
very
final
Google
as well.
Documents thing to do, wouldn't it?
Yes, because that would help out with the final as well for second semester. Because then I can go back and I can be like, oh yeah. This
So if I
is-
send it to your
Second
EVSC
semester.
email, will you find
That's
it?
what I mean. Like, at the end of the second semester, I can go back and be like, oh yeah, this is what we did in the second semester.
Ah.
Now I can look
All
at
right.
everything that we did.
Yes, I'll be glad to like put those out, the assignments on a clean spreadsheet and share that with you. If I share it to your EVSC accounts, you'll get it?
Yeah.
Yeah.
All right,
I have
fantastic.
everything linked to my regular account.
Awesome. All right, so we have that. All right, so I will do that. We will do that after we get done with the lecturing today. All right, here's the deal. Today is Tuesday. It is a week that we have a Friday. So here's the deal. We are going to do section whatever we're on, 3.8 or 3.7, whatever this is. It is implicit differentiation. We're going to do that today, and we have one more section on Thursday. Then on Friday we are reviewing, and on Tuesday we're taking a test in the room. Okay, and Scott and Joe can be here because it's spring break for EVSC at that. That's sorry for Ivy Tech, right?
Yeah.
So how does that work for you guys? Do you guys get stuck here during your spring break because Ivy Tech is still
Yep.
in?
Yeah.
Well, that's an awesome way to make it work.
That sucks.
Yes.
I need to go on the same week.
I don't know why Ivy Tech has to have it off of like everybody. Like they don't match up with USI, they don't match up with EVSC.
I don't know.
Doesn't make
Yeah,
any
because
sense.
USI is on the same as us. All the
No,
universities.
USI's having their spring break.
Yeah, it should be right now.
Oh.
Yeah, USI and U of E, I believe, have this.
No, ours.
Yeah, so I don't know
Yeah.
what Ivy Tech's problem,
I
because
don't
it's
know.
literally like signing a piece of paper and saying this is the schedule, like it's
Yeah.
that easy.
Yeah.
Never actually.
All right.
Big thing.
So here's the deal. So we do have a test on Tuesday. That's the plan anyway. Okay? And I think it's going to be good. Because even though we have learned an incredibly large amount of stuff and done a very large number of problems in this chapter, the truth of the matter is most of this has just been applying rules.
Yeah.
And that's a great thing. I mean, that's what's great about Calc 1 is you are learning a bunch of rules and just getting really fluent, to use the right term from education. You're getting really fluent at applying that to all kinds of different problems. That's a great thing. So anyway, I'm thrilled with the way this is going and so on. And then we hit today. Implicit differentiation. And this is the one that kind of tripped me up. Most of this other stuff we do a lot in like my other classes and so on. And I got no problem remembering all that I mean, we do it all the time. We don't, a lot of what we do in atmospheric sciences is, when we're solving problems, is implicit differentiation, but that's not exactly what we call it, and we use a slightly different set of steps. And so I'm not nuts about the way this is being explained. Let me see if I can help you, because what's going on in this chapter, this section rather, is a little bit of a mess. It wants us to notice something before we get going with this here. What is the difference between, like, here's something I can write on the board, and here is something else I can write on the board. And they're kind of equivalent, right? I mean, I've got something over here. I know the string is in the way, and I can't. There's no hook in this room to make it go away. All right, that'll do. I mean, these are. If you made a graph of these things, they kind of look the same. but they're different. Notice that this one over here that I have drawn on the left, this is a perfectly lovely example of an equation. I mean, x squared plus y squared equals this. But this is definitely not a function. In fact, if we made a graph of this, we would see that it makes a circle with a radius of 5. Happens to be what that graph, that equation looks like, which fails to be a function. Hey, why does that fail to be a function?
Doesn't pass the line
Doesn't pass what?
test.
Yeah, the vertical line test, right? Every place that we draw a vertical line, it either crosses no place, which would be fine for a function, not great, but fine, and it would have plenty of places where it's 2, and that's not good, right? So this is definitely not a function, whereas this guy here is. It's just a piece of this graph. You see, this one right here would be this part of the graph, which would be just fine, okay? So if we needed a derivative of this thing, well, we could, I mean, the right word here is that we would say that this equation implies, or this equation is implicit from this one. All right, now, so we're going to be looking at equations that are a bit of a mess, for lack of a better word. I mean, look at this guy right here. If I said find the derivative of this with respect to y, the derivative with respect to y, see the notation that we use here? That Leibniz notation. The derivative with respect to y of this thing, that could be a real mess. But apparently it exists. I mean, thinking back to that graph I just drew, clearly at places along that circle we would have a tangent line. I mean, there has to be something we can do here. That's the kind of problem we're solving today. This could have been something other than x's and y's. If this was an engineering problem, if this was a science problem, there would be something we could do where, like, maybe this is temperature and this is pressure, okay? The derivative with respect to pressure, like how does temperature change as a function of pressure or something like that? It could be. It clearly exists. There, just like when we looked at that graph of that circle, there's clearly derivatives. Because we could have a tangent line and those tangent lines have a slope. The question is how to get it. Now, your book on page 310, I think it is, no, 311, has a problem-solving strategy for implicit differentiation that seems to work. And I don't want to make a mess of it by telling you something different that would get you to the same place. So let's talk about what it says there on page 311 here. If you have some kind of, let's actually make a list here. I'm going to do this here. And we'll divide the board in half. And we're going to make our set of steps over there on the left, and we'll do an example on the right. Heavens, let's even do that same example over here on the right, since that's what the book does. Here's our equation. All right, and we want to find the derivative with respect to x. Okay, step one in your strategy is take the derivative of both sides with respect to x. Remember, now that step is not such a miracle because you always, whatever you do to one side of an equation, you got to do to the other. Now remember, we're using that Leibniz notation here to keep a track of what we're talking about. The derivative with respect to x. That business of tick marks gets us into a little bit of trouble here. So let's be more explicit and use the Leibniz notation. Okay, so the derivative of the left-hand side with respect to x, here's the derivative of the left-hand side is equal to the derivative, oops, it's not partial, it's total, with respect to x of 25. Okay. And this is just the derivative of a sum. So that's the same as the derivative of each of the terms separately. Hey, what's the derivative of 25? What?
0.
0. Derivative of any constant number is just 0. Okay, now here's where a little miracle happens that we have to be careful about. This is what's making me a little uncomfortable with what they're doing, but let's do it the way they're doing it. What is the derivative of what is the derivative of x squared with respect to x?
2x.
2x. What is the derivative of y squared with respect to x? Oh. The derivative of y with respect to x. Oh. This is a tricky thing. It's technically a chain rule. Because what we're going to do here is we're taking the derivative of the outside, in this case 2y, times the derivative of the inside. The derivative of y with respect to x. See, y is a function too. Y is a function of x. We could have started right up here at the very, very beginning and rearranged this thing to be y equals a bunch of stuff that had x's in it. In fact, at the beginning of the lecture, we did. It was square root of 25 minus x squared. This.
So y is on the outside as well?
Well, if this was a chain rule, if this had been the derivative of the cosine of x squared, we would know how to do this using the chain rule, right? It would be derivative of the outside times the derivative of the inside. Remember, the cosine is negative the sine, right? We would know how to do that. It was a chain rule kind of thing, right? The outside function is squared, so it's 2 times the inside function times the derivative of the inside function, right? That's what we did last week?
Right.
Right. This is the same thing, but boy, it's hard to think about this. Now we're saying the derivative of y with respect to x, well, the derivative of y squared in this case, okay, it's a chain rule thing. Derivative of this thing is 2y times the derivative of the inside. It's the derivative of y with respect to x. Which that's actually what we're trying to solve for, right? The whole point of this problem is find dy dx.
So how come it's not 2y times d times y squared over dx?
You want to put a y squared in here. It's just the derivative of the inside part, which is, like, now we're taking the derivative of y squared. Okay? So the derivative, let me clean this up. I agree, this is not such a great explanation right here that they're giving. But
So if you just move this from...
if instead of y, this had been cosine, you wouldn't have been so freaked out by it, right? It would have been 2 times the cosine times whatever the derivative of that inside part was, derivative of cosine, which is negative sine. Instead of that, it's derivative of y.
I was just looking
Yeah.
at like an x. Or
Yes.
But I was just looking at the parentheses, the placement of them
Yep.
confused me for the most part.
Okay. We'll do several examples. So look what we got. We've got 2x plus 2y times dy dx equals 0. All right. Now, step 2. Rewrite all the terms containing dy dx on the left and anything that doesn't contain dy dx on the right. Let's see. Let's put dy dx on left-hand side, everything without dy dx on right-hand side. Alright, so, let's see. So we're going to pull, let's subtract this 2x over to this side. We'll have 2y dy dx equals negative 2x. Okay? 3. 3 does not apply to this particular problem, but let's just say, if needed, factor dy dx out on left-hand side. Now in this case there already is, I mean it's just one term, it's a factor, dy dx times in this case 2y. Okay? So in this case this doesn't happen. But there could have been a term here where, like, you know, there was other things going on and we had to factor that dy dx out. And then I'll just say algebra to get dy dx equals something. So like I could then take both sides divided by 2y to get dy dx, the derivative of y with respect to x, equals, in this case it works out to negative x over y. And that, believe it or not, is our answer. Notice what happened here. The derivative depends on both x and y. See, remember, like for example in this one, it was the graph was a circle. The derivative at some place depends on both what value of y you're at and which of the two, you know, like if we were at this value of x, it depends which of the two y's. Or if we're talking about at this value of y, there's two values of x that it could be at. So you have to know both, it depends on both the x and the y in this case. But this method here is how we're going to be doing this implicit differentiation. And once we get going doing it, it's not going to be that hard, but we got to do a couple of examples to make it through all of this. Alright, now, I want to see here. Man, all these examples they have here do so many steps. Do we have a simpler one? No. So, let's try one over here. We'll leave our steps up, and we're going to try another equation. Alright. Here's our equation. X cubed sine y. So given x cubed sine y plus y equals 4x plus y equals 4x plus, I think it's 3, it doesn't matter. Yeah, 3. Find the derivative of y with respect to x. I don't know if this book even gives us a graph of this thing. No, it doesn't in that particular case. Doesn't matter. We should be able to apply our rules to this and find that derivative. So this thing is something, it's clearly an equation. It has graphs, but apparently it's not a function. If we actually made the graph, it's an ellipse or something. So let's apply our rules and see what happens. Here's our equation, and our first rule is take the derivative with respect to x of both sides. So we're going to take the derivative with respect to x of this side. Well, let's be more explicit about it. And the derivative with respect to x of the other side. The right-hand side doesn't look so bad at all. In fact, why don't we go ahead and do that right now? The derivative with respect to x of 4x plus 3. Eric, what is the derivative with respect to x of 4x plus 3? This is just a power rule, whatever kind of thing. The derivative of 4x plus 3 is 4, right? Alright, because the derivative of 4x is just 4, derivative of 3 is 0. Right. Right. Alright, so that right-hand side is no big deal. The left-hand side is where all the problems come around. Alright, so let's see. This is a sum, which means we get to take the derivative of this piece plus the derivative of that piece. Let's even be very careful about that and write that out. We get to take the derivative of this piece plus the derivative of the second piece. Hey, that's one of the things we're trying to solve for. Dy dx is equal to, and then the right-hand side is just 4. All right, derivative of this thing with respect to x. Hey, that is just a product rule. We've got a thing times another thing. That's the product rule. All right, let's be even very clear about this. It's the derivative of the first term times the second term plus the first term times the derivative of the second term. And then the rest of this equation here, dy dx rather, equals 4. See what happened here? We just very carefully wrote out the product rule. Alright, the first one is not so bad. The derivative with respect to x of x cubed is, Matt, derivative of x cubed is?
2x.
No.
Oh,
3x squared.
Yeah.
Times?
I was looking at it too.
Sine of y, I know you were, yeah. Plus x cubed. Alright, now the derivative with respect to the sine of y. What's the derivative of sine of y? Cosine of y times the derivative of y with respect to x. Again, it's a chain rule kind of thing. Alright. Derivative of sine of y is derivative of the outside part, sine, which is cosine, y, times the derivative of the inside part, which is just dy dx. Plus, and then the rest of this equation here. Alright, we have done step 1 thoroughly. Probably should be looking on the screen to see if I'm doing it right, but we're going to try it. Step 2, move everything that has a dy dx to the left-hand side, move everything that does not have a dy dx to the other side. Well, I see that x cubed cosine y dy dx plus dy dx equals negative 3x squared times sine y plus 4. All the terms that have a dy dx in it are on the left-hand side. Everything that doesn't have a dy dx is on the right-hand side. Sounds like we're following our rules so far. And then we just algebra it until we get... Oh no, wait. First our rule 3. This time we do need to factor. Look, we've got a dy dx in both of these two terms. dy dx is x cubed cosine y plus 1. How horrible did they want this thing? Okay, we're so far so good. Yep. And then we're just going to divide both sides by 3x. Now let's just get everything else using algebra over to the other side. So it's the derivative of y with respect to x times this thing. So let's just say the derivative with respect to y, the derivative of y with respect to x equals, just so we're writing it in the same way they did on the book, we'll rearrange those two terms. And shockingly, that is what they want. We have solved so that the derivative of y with respect to x is something. I don't know what that equation looks like. I mean, as far as what a graph looks like. But now we know, heck, maybe the graph even looks like this squiggly thing I just drew here, right here. That sort of cloud-shaped thing. If that's what the graph of this horrible thing looks like, now at any given place on there, x, y, we could find the slope of the tangent line by this implicit differentiation. The actual technique, as long as you go through all these steps really carefully, is not so bad, except remembering this trick. When derivative of something with respect to x, where the inside has a y, you got to remember that dy dx thing. Let's do another one. I don't like this second derivative problem here. Let's see if we can find another one. On page 314, problem 3.75, example 3.75. It has a great looking little graph that's called the leaf of Descartes, or the folium of Descartes or something. It's a famous graph. It kind of looks like a leaf. And in that problem, they say the equation of that graph, the folium of Descartes, is y cubed plus x squared, no, plus x cubed, minus 3xy, yes. Is 0?
Yes.
Yeah. Okay, so if you haven't looked at it in the book, it makes a graph that looks kind of like this. It's kind of pretty. It makes like a little loopy thing. Folium is, I don't know, Latin for something like leaf or something. And they wanted, okay, they actually want you in this equation to find the equation of a line tangent to, okay, let's not worry about that right now. Let's first worry about finding the derivative of this. So given that this is the equation that you are having, this is clearly not a function. This thing clearly fails to pass a vertical line test. This is not a function. But that doesn't mean it doesn't have a derivative. Clearly at any point along there, there's got to be some kind of tangent line. Let's follow our rules. First rule was take the derivative with respect to x of both sides. So it's the derivative with respect to x of the left-hand side equals the derivative with respect to x of the right-hand side. Well, that's easy. Derivative of 0 is just 0. Okay. This is a sum. We got 3 terms added together here. So it's the derivative with respect to x of that first term plus the derivative with respect to x of that second term minus the derivative with respect to x of that last term. I'm going to pull that negative sign out there in front. Equals our right-hand side. Okay. The derivative with respect to x of y cubed. That's a chain rule thing, because y is a function of x. We could have rearranged this thing. We could have done some factoring or something and made it y equals a giant mess that involved x's. Y is a function of x. So the derivative of this is going to be 3y squared. Just like if this was the chain rule. If instead of y this had been sine, we would have had no trouble saying that this is the derivative of this is not. Okay, so if the function had been sine cubed, we would have had no trouble saying that was 3 sine squared. Now we're saying it's 3y squared, but then we have to multiply that by the inside of the function, which is dy dx. The derivative of the inside. Plus the derivative with respect to x of x cubed. That's easy, that's just 3x squared. Minus this is going to be another product rule. 3 times derivative of the first, derivative of x with respect to x is 1, times the second, plus the first, times the derivative of the second. Lots of simplifying here. 3y squared dy dx plus 3x squared minus 3y minus 3x dy dx. What a mess. Okay? Oh no, we're on to step 2 now. Put everything with dy dx on one side, everything without dy dx on the other. Alright, this guy's got a dy dx, and this guy's got a dy dx, so let's put them on the left-hand side. Everything else goes on the other side, so let's see here. Minus 3x squared plus 3y. Both of the terms on the left-hand side have a dy dx, so we got to do that optional step 3 there, where we factor out the dy dx. And then we just use algebra to move this term over to this side. And you get dy dx equals this mess. Oops, that's y. And that's our answer. Let me just double check if we got the right answer for the derivative. Derivative. Plus 3y minus 2 minus x. Yes. So that is the derivative of this. At any place along the way, on the leaf of Descartes, we could have said, let's say at this spot right here. This place right here has some value, x, I will call it x1, y1. That location right there on the leaf. It has a tangent line that has a slope, the slope of the tangent line, which is equal to this thing. Now we'd have to plug in x1 and y1 into it, but we'd have its slope. That's what the derivative is. And if we were at the same value of x, but we had a different value of y, like we were at this part of there, we might have a different tangent line going through there. That's not a very good tangent line, but you understand what I'm drawing right there. And don't forget, I was talking to some of those other guys who are doing the class independent study, don't forget, if you have the point and you have the slope, you could use that point slope form to get the actual equation of the line itself, that is that tangent line. Remember, y minus y1 equals the slope of the tangent line times x minus x1. And then you'd actually have the equation of the line itself, which some problems ask for. This one in the example book, the book does. This is just going to take some exercise. And I think the best way for us to move forward on this is to just do the assignment and work on them. Yeah, math.
So would this derivative only work for that loop?
No, it would work anywhere in here.
Anywhere?
Yeah.
Alright. And then if you use the regular one without going through this, it wouldn't work on the loop.
It wouldn't work anywhere because this function here too, you're right, like from here to here, strictly speaking, this is a function, right? Right, like in this range. How do I want to do it? So, you could take this equation right here and rearrange this until you got y was equal to something.
Right.
And you could then take its derivative in this range, and I think it would be fine. My guess is that it would be harder because you'd have like all kinds of crazy terms. I mean, there would be cubed roots in it and stuff like that. Right? This would be a mess fast. Believe it or not, this probably is the easier way for a problem for this form. Mm-hmm. Yeah, but no, you're right. This would apply everywhere in here, not just through the loop. All right, great question. All right, let me pull up. Where'd the problem set go? Okay, for today. Like I said, I suspect we're going to need to talk about some of these guys as a group. All right, so what is today's page? It's page 317. 317. We need 301 to 315 odd. And then, just one more problem. I think it's 323. 323 looked interesting to me, but I have to admit I haven't done it yet. It's a story problem kind of thing, application, and I haven't done it yet, but it looked interesting, and so we'll try it. I mean, if we can't get it to work, we can't get it to work. All right. All right, guys, work on that for the next half hour or so, and I'm gonna get this stuff uploaded. Okay.